Something quietly happened in June 2025, and most people completely missed it. A powerful new telescope in the mountains of Chile began testing its systems, and within only a few hours, it started revealing objects in our own solar system that humanity had never seen before. Asteroids. Distant objects beyond Neptune. Near-Earth objects. And eventually, evidence of a visitor that had come from another star system. And the most incredible part? This was before the Vera C. Rubin Observatory had even begun its full scientific survey. The observatory sits high above Chile's Atacama Desert, one of the driest and darkest places on Earth. After more than 2 decades of development, Rubin was built for one extraordinary purpose: to repeatedly photograph the changing universe and create the largest time-lapse record of the night sky ever attempted. At the heart of the observatory is the LSST camera, one of the most powerful digital cameras ever constructed. It has about 3.2 billion pixels. For comparison, a typical smartphone camera has only a fraction of that resolution. The camera itself is enormous, roughly the size of a small car, and a single exposure can capture an area of sky far larger than the apparent size of the full moon. But Rubin isn't simply designed to take beautiful pictures. It's designed to notice what changes. An asteroid moving across the sky. A star suddenly becoming brighter. A supernova exploding in a distant galaxy. A black hole feeding on surrounding material. Or an object appearing where nothing was visible before. The observatory is named after Vera C. Rubin, the astronomer whose observations of galaxy rotation provided crucial evidence for dark matter. She discovered that galaxies were rotating in a way that could not be explained by their visible material alone. Something invisible appeared to be supplying additional gravity. We now call that mysterious material dark matter. It doesn't shine. It doesn't reflect light. And despite decades of experiments, scientists still don't know exactly what it is. Rubin's work helped transform that mystery into one of the biggest unanswered questions in modern physics. And now, the observatory carrying her name is going back after that same mystery. During its early commissioning observations, Rubin detected thousands of previously unknown objects in the solar system. Among them were main belt asteroids, objects beyond Neptune, and near-Earth objects. And scientists expect that number to explode once the full survey is underway. Over its planned decade-long mission, Rubin is expected to discover millions of small bodies throughout our solar system, dramatically expanding the known population of asteroids and other objects. Some of them could pass relatively close to Earth. That means Rubin isn't only helping us understand the distant universe. It's also creating an enormous new inventory of our own cosmic neighborhood. Then came one of the strangest objects found in the early data. Researchers identified an unusually fast-spinning asteroid designated 2025 meganewtons 45. The object is hundreds of meters across, yet observations suggested that it completes a rotation in less than 2 minutes. That's astonishingly fast. Large asteroids are often thought to behave like loosely assembled piles of rock and rubble. If one of these objects rotates too quickly, centrifugal forces can overcome its weak gravitational binding and cause it to break apart. An object rotating this rapidly therefore raises an important question. What is holding it together? One possibility is that it has far greater structural strength than an ordinary rubble pile asteroid. Another possibility is that it represents a fragment of a much larger body that was shattered during a violent collision in the early solar system. Whatever the explanation turns out to be, discoveries like this give scientists a rare opportunity to study the hidden internal structure of asteroids. But Rubin's early discoveries weren't limited to objects from our own solar system. During its commissioning observations, the observatory also captured images of 3I, Atlas, the third confirmed interstellar object ever detected passing through our solar system. Before 2017, humanity had never confirmed an object originating from another star system. Then came Oumuamua. A few years later, astronomers discovered 2I, Borisov, an interstellar comet. And then came 3I, Atlas. The remarkable part is that Rubin's early images showed the object before its discovery was officially announced. Astronomers were able to go back through the commissioning data and identify earlier observations of the visitor. That means Rubin was already watching an interstellar object before the astronomical community knew it was there. An object like this is effectively a sample from another planetary system. It formed around another star, was eventually ejected into interstellar space, and spent an unknown amount of time traveling through the galaxy. Then, by pure chance, its path brought it through our solar system. Scientists believe interstellar objects may pass through our cosmic neighborhood far more often than we realize. The problem has always been finding them. They're small. They're faint. And they move. Rubin was specifically designed to solve that problem. And 3I, ATLAS may only be the beginning. The observatory is expected to discover additional interstellar visitors during its long survey, giving scientists opportunities to compare material formed around completely different stars. Then there is another extraordinary capability. Rubin's automated alert system can notify astronomers whenever something changes in the sky. During early operations, the system demonstrated its ability to generate hundreds of thousands of alerts in a single night. Each alert can point scientists towards something potentially important. A new asteroid. A variable star. A supernova. An active galaxy. Or an event nobody expected. One of the most intriguing possibilities is the search for failed supernovae. When a massive star reaches the end of its life, we normally expect a spectacular explosion. But theory predicts that some massive stars may collapse directly into black holes without producing a conventional supernova. The star could simply disappear from view. No enormous explosion. No brilliant flash. Just a sudden collapse. Astronomers have candidates for this phenomenon, but definitively proving that a massive star disappeared into a black hole without exploding would be a major breakthrough. Rubin's greatest advantage is repetition. It will keep returning to the same regions of sky, allowing scientists to compare images over time. That makes it possible to detect changes that a conventional telescope might miss. But all of these discoveries are only part of the larger mission. Rubin is ultimately designed to investigate some of the deepest mysteries in cosmology. About 95% of the universe is believed to consist of dark matter and dark energy. Everything we can directly see, from stars and planets to galaxies and ordinary matter, represents only a small fraction of the cosmic total. Dark matter appears to provide additional gravitational mass. Dark energy appears to be connected to the accelerated expansion of the universe. But we still don't know what either one actually is. Rubin will attack these mysteries by mapping billions of galaxies and studying how their light is distorted as it travels through space. That technique is called weak gravitational lensing. Dark matter cannot be photographed directly. But its gravity bends the light coming from objects behind it. By measuring those tiny distortions across enormous regions of the sky, scientists can reconstruct a map of where dark matter is concentrated. It's like trying to see an invisible object by watching the shadows it creates. Rubin will also study the large-scale structure of the universe. Galaxies aren't randomly scattered through space. They form enormous cosmic filaments, sheets, clusters, and voids. That structure contains information about how the universe evolved and how dark matter and dark energy have influenced its history. The full survey is designed to continue for roughly a decade. Night after night, Rubin will repeatedly scan the southern sky. Over time, those observations will create an enormous movie of the universe. Not just a static photograph. A record of change.